Hello, thank you, Rodrigo. I'm very happy to be presenting today and to be also receiving, all the information from the presentation of the previous speakers, which was very interesting. I will share now my. So tell me if you are seeing. So it's seen correctly? Yes, the screen.
Yes, very clear.
Okay, so basically the objective of the talk will be divided into parts, which are basically two applications of remote sensing, computer vision, and machine learning to agriculture and farming. I will be doing a kind of double representation of with a double affiliation, because some of the work I will be presenting was done with the company, and some other part of the work was done with the university and in collaboration with the university. So basically, these are the two affiliations that I have, and I will be presenting kind of a combination of both in this presentation. So the first one is related to case one, which is a national crop sustainability monitoring system. As you may know, Uruguay is an agricultural country. 25% of the GDP comes from agriculture and farmers' activities, and nearly 80% of exportation is come also from there. So there was a very strong need to present, to create, or to manage correctly the different components of a production, of agriculture production, in particular soil. So in 2013, the Uruguayan government create a plan in which all farmers has to present what they will be doing in the field, the different crops they will be doing and how they will be doing those crops in order to preserve soil. So basically what we developed was this system to enable the farmers, the technical engineers of the farmers, to present the plan, which is basically composed of two different elements. One is a geographical polygon that describe where in Uruguay that plan will take place, and also what the farmer will be producing in there. So, for example, here you can see the kind of polygons that were drawn by the technical engineer, and also what the different crops that were being executed during those periods of time. The system also has a capability to validate the plan and also to monitor the plan. So basically, the validation of the plan was based on what is called the Usler-Rusle equation, which is an equation that relates the estimated soil erosion, which is this value A, with the natural regeneration rate for the selected soil type. So basically, there are like five factors that are taking place in this. Three of the factors, which are the K factor, came from the soil, and it's obtained from already computed soil maps, and the R factor, which is the rainfall erosivity, which is also built and obtained from other layers of information that the Ministry of Agriculture has in Uruguay. So basically, once the technical agriculture create the plan and draw the polygons in the plan, these two factors are computed automatically. The third factor related to the geographic situation of the polygon is what is called the LS, which is based on the critical path, which is, the worst slope and length that is presented in the polygon. So, and this is again, it was computed automatically. So with these 3 components, there were only 2 which were management, which are the P, which relates to how the farmer is considering to do the management of the crops, and also the C factor, which is obtained from the different crops which are presented. So basically, all that information is once we have all the information is computed, and only if the equation, if the factor A is lower than the T, which is what the soil can support, is the plan allowed to be presented. So there are a number of rules that were fired. Even if the technical agriculture has also the ability to change some of the automatic values. For example, the soil, because soil, they may have a better determination of the type of soil which is in their field. So they may change the automatic K factor with a manual one, but they have to justify that. So they have to present, for example, a report or an analysis of that information, and that change between automatic and manual is then highlighted for the ministry, for the technicians from the ministry to see those changes and realize if there is anything wrong with the change. So basically, there is once the plan is presented, there is a kind of validation from the side of the government. And once the plan is completed, it comes what we call the monitoring of those crops. So because you can say that you will be doing, I don't know, soybean and then plant 1 year of grass, but that has to be monitored, and for that we use remote sensing and images, in particular based on NDVI. Basically, what the system does is to run a classification process all over the fields and determine if what we are seeing is or not it is or not it's not the corresponding field. And they also have the possibility to define a threshold on the value to be applied. It was a very simple monitoring tool, because we don't. It was in fact not a classification algorithm. It was just based on a threshold on the NDVI for a specific time, which is basically with that classifies basically if there is a crop or if there is no crop at all. As a second part, and this is something that we just finished the last year, or this year, in fact. So we start working on really monitoring and mapping the agricultural crops in Uruguay. This is a work done by Adrian Cal with the supervision of Pablo Musea and myself. This is his master thesis work, and basically, and it was done in the University of the Republica. And basically, the idea was to study to do kind of what I have explained before, but in a better way, in a proper way. Not just saying that if there is a crop or not, but trying to really classify what kind of crop is presented on each one of the fields. So the objective of the study is to develop a classification algorithm in particular for summer crop. This is basically because summer crops has a far more area in Uruguay than winter crops, in particular because of soybean. And so we focus on that, but the idea is to extend obviously this work for winter. But today I will just present what we have completed, which is for summer. It is important to keep in mind that Uruguay, nearly 10% of the country area is used for agriculture activities. So it's a very, very big percentage of the country, which is apply use it. I mean, which is doing agriculture. So for this study, we have we have two data sets. One is this data set of what I previously present to you, which is the declaration of the different farmers. That is basically 1.5 million hectares, and it's composed basically of pasture, soybean, maize, sorghum, wheat, barley, and sorghum maize, which is a kind of a secondary class. And it goes through 6 seasons, and is a very unbalanced data set because of the, as I presented before, because of the soybean. The other data set that we use is one obtained from a cooperative of farmers. It is nearly 1,200 farms, which is what we consider our ground truth, because the previous one, the data set from the ministry, MGAP data set, it's a declaration, although it has to be a formal declaration, and there are penalties if you don't declare, if you don't do what you are declaring. We cannot trust 100% on that data set. So basically, the main components of the solution was to base the classification on satellite images. For that, we work with optical and radar images. We also based our analysis on time series, not only on one snapshot in one specific point of time, but on all along the crop duration. And in particular, it was used we implement a random forest classification technique. The data that we have used is Sentinel-2 and Sentinel-1. The time period was between October to May, which goes to sown to harvest. And well, we use basically the Google Earth Engine to process all the images, which is it proved to be a very good approach because Google Earth Engine has a lot of tools to work with the images. Well, first of all, we did a kind of analysis of the different type of data. So we basically test everything. We test optical data, and we test radar data, and we also test combinations. And I am just, so in this graphic, you can see the different bands and also the different combinations for the three, for soybean, sorghum, and maize, and also the average. And I just highlight here only the 3 most higher values that we have obtained. Basically, obvious, I mean, this is not obvious, but using all the information, we obtain the best results. But you can see that in the 3rd place, and only with a 0.5, just NDVI and AVI and SAR already has a very good performance in terms of F1 score. So that means that it may not be necessary to use the entire set of data. In any way, for this study, we use everything we have. The other thing that we did is to because we are working on time series, so we perform a temporal interpolation of the data. We have selected basically to do it like each between 16 days. Normally, SAR images and Sentinel-1 and Sentinel-2 has a shorter visit time, but we keep on these 16 days because we believe it's a good compromise between the number of features of the final vector and how the different crops grow within the time. So 16 days is something which is a good value to sample. Well, we also did some other image processing task. We with the noise SAR images with the speckle algorithm, just a very simple median filter. And finally, in order to obtain the data, what we did was to sample at every 1 hectare. So we basically take the polygons of the data set that we have, and for that polygons, we sample each 1 hectare the points, and we extract for each one of those points, we extract the entire bands of the both images. We compute also NDVI and AVI, and we, because it is a time series, we take 15 samples. So basically, we have for each point vector, we have for each point, sorry, we have a vector of 210 features, 15 time and 14 bands. With respect to the MGAP, which is the data from the ministry, because it is a declaration, and although it's formal, it may still have errors, we have decided to do a cleaning of the data. So we run a clustering process to select the clusters to obtain the digital, the NDVI signature of each one of the clusters. So we basically create clusters and then analyze the signature of the NDVI. And we basically remove at hand those that are not related to what is known to be the signature, for example, for soybean. So here, for example, you can see that this violet signature has nothing to do with the natural or the usual way a soybean crop performs, which is to start very low, go higher, and then goes down during the harvest. So we believe that this, for example, this one should be grass or bare land. I guess it is more grass. But in any way, we remove those clusters from the data set. The other thing that we did was to also remove points that are farther than a given threshold, which in our case is 75%. And this is only for the training purposes. Well, the other thing that we did was to search for different algorithms. So we test basically 4 random forest bootstraps, super vector gym, and AdaBoost. Sorry, and extreme gradient boost. And at the end, we select random forest with 300 trees, and using bootstrap, max number of features of square root of the number of features, which is 210, and also a mechanism to balance the unbalanced class that we have. Okay. Once we have, so basically we run 3 experiments with this configuration. The first one was using only the farmer's dataset. That is because it's the only dataset for which we can be sure that we have a ground truth. So we divide the dataset between 70% for training and test and 30% for validation. We use a 5-fold training set configuration. And for each farm, and to do a classification, because we may have more than 1 point for each farm, we decided to do a majority vote. And this, and you can see on the table in the right, the precision recall and F1 score of each one of the crops. So you can see that we obtain a very good precision, but the recall both for the corn and sorghum was not as good as expected. One of the reasons of this may be the small number of points that we have for sorghum and corn, because as I mentioned before, these crops are not used. Has a very, very little area compared with soybean. The second experiment that we ran was to the in the ministry dataset. So we divide the dataset again as we divided in experiment one, because we have, I mean, a very huge number of soybean. We decided to subsample soybean in order to have a better balance configuration. So we basically end up with 10,000 points per class. Again, classification was done using majority vote, and I think we obtained very good results using only this dataset. And finally, we run experiment 3, which is we train with the farmers, with the entire farmers dataset, and we test with the ministry dataset, with the Ministry of Agriculture set. So what we can see from the table in the right is that we again obtain a very good precision and recall for soybean. But the recall for sorghum and corn was indeed very, very low. But the precision for sorghum is not, again, also the precision for corn and sorghum is not as good as expected. So there are basically two reasons for this. The first reason is that because we don't know exactly what are the real what is really done at the ground, the data from the ministry may be wrong, and that assumption, which is that we have mislabeled crops in the ministry dataset, is something that we believe is making this difference to happen. The other difference, which is also very important, is that the information that we use in this experiment to train for sorghum and corn is very low, because we use only the information of the farmers. So basically, what we intend to do in the next part of this project is to increase the levels for corn and sorghum on ground truth, so we are sure that we have corn and sorghum, and also run these same experiments on winter crops, which are also important for the management of the soil in Uruguay. So this was the first case that I wanted to mention to you. I want to highlight again that this system is already in place. It is in place since 2015, and it is basically managing and monitoring the entire agriculture activity of Uruguay, at least for bigger surfaces, and it is a way that the country found to monitor and to preserve soil, and to implement good practices for the soil. The second case that I will present is a very different one. It is an application that we developed within the company to automatic count ships from drone images. So we followed two approaches for this. The first one it was based purely on image processing. So we start doing classical image processing work, like doing white balance, adjusting light conditions to have a kind of or to reduce the variable of the images with respect of lighting conditions. We then run or implement a very simple front background segmentation based on graph cuts, which creates a kind of first mask for which we can say, okay, there is no ship on this mask, which is the background, and there is a probability to have a ship in the other mask, which is the green one. So here you can see some examples. You can see, for example, that here this forest, these small trees are considered in the case of as if they were ships. Here again, there are a lot of background which is incorporated to the mask. And then we run a second for that mask. We run a second segmentation algorithm based on the size based on the form, and based also on the color of the ship. So here you can see a number of some of results of this segmentation, and then basically starting from that segmentation, we perform a counting. But again, we still have very bad results on some part of the image. So we decided to move to a more machine learning, deep learning approach. But so we developed an app to tag the ships, but we use our image processing approach to do a first initialization of the value, and this helped a lot during the training process because it reduced enormously the amount of work for the person who has to tag for the ships. So the conclusions of the image processing was that, in overall, it has a precision of 73 and a recall of 81, but it was not what the client was expecting. It was so the client was expecting more, nearly 90% of precision and recall. So we decided to move. So basically, there are two main issues with the approach. Some of the segmentation between background and front was not good enough, and some ships were counted twice because of over segmentation. So so we moved to the next approach, which is to use a faster Bayesian convolutional neural network. So faster Bayesian convolutional neural network, in fact, region-based convolutional neural network are basically a two-step process. First of all, there is a process to select regions to be later on classified, and the output is at the end a bounding box and a class. In our case, it's ship or no ship. So we find out that this method was very accurate, but for our purposes, very slow. So here you can see some of the outputs of the method. More examples. And more examples. You can see the difference between also the difficulty of the background. It's sometimes are very, very green, sometimes are on a soil with stones and rock. Sometimes so it's very difficult it's a very difficult task, or it was a very difficult task. Even those in the shadows, it's also difficult to manage. But we obtain a better precision. We reduce the recall in this case, but basically the basic issue was that the model was too big for a mobile app, because this has to be a mobile app, and it was too slow, between 5 to 6 minutes per image. And because the image was processed entirely, ships were too small, and because of that, the model was not good enough. So the results at the end were under what we have expected, and especially bad for groups of ships. So we move to a third approach, which is single shot detector. In this case, this is another network which does not need a first step regime proposal. It does all in one shot. And in particular, it processes the feature maps at different scales. And the function loss is a combination of the localization and the classification problem. With this, we also changed the architecture of the system. So instead of processing the entire image, we decided to process by tile. We also changed this. This change also has an impact on the user experience, because tile processing gives us also the ability to show the results as they were processed to the user, so the user can start to fix any issue or any problem that they may found with the automatic process. Well, with this SSD net and using Inception as the feature extractor, we obtain a precision of 90% and a recall of 84%, which is quite an improvement from the previous one. But we have a lot of, I mean, the model was much more smaller, 30 megabytes against 250, and much more faster, 1 or 2 minutes against 5 and 6 from the previous solution. The tiling and the tiling also enable us to do multiple execution, which enable us to increase the ship size and improve the performance. So, and the final implementation there was then to use this single shot detector with a mobile net for extractor, and the final results were a precision of 91% and a recall of 96%. Here you can see some of the worst cases of the application. You can see that basically there are a couple of ships in there that are not well segmented. Here you can see that there are also some other missing ships. And again, some other ones. And the best cases are basically cases where all the ships were detected. So this application was developed for the Uruguayan it's like an organization that Central Lanera, which is an organization that keeps all the information from different ships producers, and it's available on Android, so you can test it if you want. And that's it. I mean, these are the two applications that I wanted to present to you. Both applications are running and are in production. So I think these are good examples of the use of computer vision, image processing, and machine learning to real productive agriculture and farming activities. And I will finish with an invitation for you to also see the presentation on Wednesday from Matías Tailanian, a colleague from Uruguay, which we will present in a case for the forestry industry for automatic application of herbicides using computer vision. So I think that will be very interesting also for you to take a look at that. Thank you very much.